Hello and welcome back for lesson 8.3. We are going to learn how to officially run our own hypothesis test. Super exciting. So in this lesson, we're going to learn how to state the 6 steps in a hypothesis test and how to test specifically for quantitative means data when the sigma is unknown. So we're assuming the sigma is unknown, and we're going to be using the t-test. So here we go. These 6 steps are what you're going to be expected to show in your chapter 8 project for me, as well as on the final exam. So the first step is to state the hypothesis. The second step is to state the level of significance. The test statistic or the p-value is the third step. The fourth is the graph of what this looks like, either the test statistic or the p-value. The fifth step is the decision, and the sixth step is the conclusion. Also remembering, we just talked about in the end of the last lesson about the t-test statistic, and it should look pretty familiar like a z-score. It's called a t-test statistic because it goes along with quantitative data. We're going to take the sample means and subtract the population mean and divide by the standard deviation divided by the square root of n. And we have to know the degrees of freedom, which is n minus 1. Okay, so we're going to first get practice doing some of the little pieces again from the last lesson 8.1 before we actually perform the first test. So let's say we had a test that was the null hypothesis was mean equals to 10, and the HA was the mean is less than 10. Assume the p-value was given to you at 0.0935. What type of test is this? So just saying we were given this, to be able to tell what type of test it is, we're looking at the HA. And so because it's a less than, it's called a left-tailed test. And a picture of this would be 10 down here, and the p-value would be written up here, 0.0935. Okay. So just from what we've been given, this would have been our step 1, the hypothesis. We would have been given the p-value in step 3, and then this is what our picture would look like. And that's all we know so far. Let's look at example 2. This time, the hypothesis was, this is a strictly greater than. The mean is equal to 1, and the hypothesis is that the mean is greater than 1. You've been given that the p-value is 0.1243. What type of test is this? So because it's a greater than, it's considered a right-tailed test. And we would draw the picture for this. We would mark 1 and then shade to the right because it's right-tailed. And then our p-value would be the area right here. Okay, example 3. Let's say you've been given that H0 is the P is equal to 0.5, HA is P is not equal to 0.5. The test statistic is 2.56. What type of test is this? So it's a not equal, so we're going to say it's a two-tailed. Two-tailed means that we have 2 markings. Our alpha would be divided by 2. We don't know the alpha it doesn't look like it's given to us, but we can find the alpha from here. Okay. So because it is two-tailed, we know that from the hypothesis statement. Then we know that 0.01 is equal to alpha divided by 2. We've already divided it by 2 because on a two-tailed, the alpha is split into 2 sides, kind of like the confidence interval. So to find out what alpha is, if I multiply both sides by 2, I can find alpha. So alpha in this case is actually 0.02. Okay, that's how I could find that if I wasn't given the alpha. And they found the critical Z value for us is plus or minus 2.33. So it's a negative 2.33 over here and a positive 2.33. And these right here, this is a danger zone and that is a danger zone. So if our test statistic is in one of these areas, we're going to reject H0, okay? And if you notice, our test statistic right up here is 2.56, and it is in this danger zone. It's over here. So we do reject H0. So because test statistic, which is 2.56, is greater than our critical Z, which is 2.33, we would reject H0. Okay, ready for our first little hypothesis test. This one here, example 4, I've actually written everything out for you, and we're just going to kind of go through it together so that you can see how this works. Okay, so it says statistics students believe that the mean score on the first statistics test is 65. A statistics instructor thinks the mean score is higher than 65. He samples 10 statistics students and obtains the scores here. So my step 1 is my hypothesis statement. So we're going with what they think is true, mean is 65. We're testing it because the teacher thinks it's higher. So that's going to be a right-tailed test. Okay, notice it's right-tailed. So down here on our picture, everything's going to be done on the right because it's right-tailed. Step 2, he performs a hypothesis test using a 5% level of significance. So level of significance is equal to alpha. Okay, so it's 0.05. The test statistic, what they did was they took the sample and found the sample mean to be 67. So we put that into our t-score here, subtracting what they think is true, 65, divided by the standard deviation. So also done in Desmos, the standard deviation of the sample means is 3.1972. And then they divided by the sample size of 10. And so our test statistic is 1.978. Okay. So therefore, our distribution that we're going to use is a critical T distribution. And because n is 10, our degrees of freedom is 10 minus 1, or 9. Okay. So calculate the p-value using the student's t distribution. The p-value x bar greater than t0 equals 1.978. So we want to find out the probability of the sample mean being greater than 1.978. That comes out to be 0.0396. Okay. So I'm going to show you what the critical T value is. I found that in Desmos here. It's saved, and I saved this particular one. It's at the end of the program here. I'll show you this in just a minute, but it's at the bottom of this. It's saved in Canvas. Inverse CDF of the D distribution, 9 degrees of freedom, 1 minus 0.05, because 0.05 is our alpha, and so our critical T is 1.833. Okay, now I'm going to go back to my paper for a moment here. And I'm going to show you where we got the p-value. So interpretation of the p-value. If the null hypothesis is true, then there is a 3.96% chance that the sample mean is 65 or more. Okay, that's smaller than 5%. So in step 4, we would draw it here. So the p-value is 0.0396 bigger than 65. That's the probability. Now I'm going to show you in the program. So if you go to the Desmos program for means, if you click on this example in Canvas too, you could just save this and then just reuse it. It's only use this when the population standard deviation is unknown, and this is for sample means. So I put in my sample size of 10. I put in the M, what our sample mean was 67, our sample standard deviation 3.1972. I put in the H0, which is 65. It gave us our test statistic, 1.978, and I changed our alpha, 0.05, and then I went down, and there's all the drop downs. Now, the first drop down we just used in chapter 7 for confidence intervals. That's chapter 7, I mean. But we are going to go down here, and we're going to choose the greater than one, because ours is a right tailed. There is our p-value. The probability is 0.0396. Okay, so we drew our step 4. Now step 5 is our alpha is 0.05 and our p-value is 0.0396. So since our p-value, which is 0.0396, is less than 0.05, p-value is less than alpha, we reject H0. So right here, at a 5% level of significance, the sample data shows sufficient evidence to support the case that the mean average test score is more than 65, just as the math instructor thinks. Okay, so there is sufficient evidence to believe that the test score is more than 65. We can also use the critical t-value because our test statistic of T0 is 1.978 is greater than the t-value, our critical t-value, which was 1.838. We reject H0. So it doesn't matter if you use the p-value or you use the critical t-value versus your test statistic and look at the danger zone. Both will give you the same result. They will never go against each other. So using the program that I had you save in Desmos will give you the p-value, which is nice. Okay, let's look at example 5. Our first one on our own. So example 5 says, it is believed that a stock price for a particular company will grow at a rate of $5 per week. An investor believes the stock won't grow as quickly. The change in stock price is recorded for 10 weeks and are as follows. $4, $3, $2, $3, $1, $7, $2, $1, $1, $2. Only one of these is over 5, so I'm not sure. I'm kind of in green with the investor. It says it won't grow as quickly, so it kind of makes me think of a less than. Perform a hypothesis test using a 5% level of significance. State the null and alternative hypotheses, find the p-value, and state your conclusion. And I said be sure to show all 6 steps. So step 1 is my hypothesis statement. And because we have units, we are talking about means. And they think it's a change of $5. But the investor thinks it's not growing as quickly. So he thinks it's less than 5 per week. Step 2 is our alpha, which they said it was a 5% level of significance. Step 3 is our test statistic. And so in Desmos, I found that our sample mean is equal to 2.6. Standard deviation is 1.8379 and n equals 10. So I can find my test statistic by taking 2.6 and subtracting 5 divided by 1.8379 and dividing by the square root of 10. I can do that, but I can also use the program in Desmos. So I'm going to go to, we're going to validate this both ways here, just so you can learn both ways. So because it's a less than, it's a left-tailed test. Okay. So we're going to look at the p-value compared to alpha. And we're going to look at this danger zone. So our we're going to look at our T0, which is going to be our test statistic. And if our T0 is greater than, or I should say, in this case, it's going to be less than because it's going to be a left tail. So if our T0 is less than out here, our T alpha. So T alpha in degrees of freedom, and ours is 0.05, and degrees of freedom is going to be 9. So let's just head to Desmos. And I am going to go to up here. Sample is 10 still. And our sample mean was 2.6. What we're testing against is 5. Our standard deviation is 1.8379. And I am saving this for you all here. And this is the stock price. And there is our test statistic. It comes out to be a negative 4.129. And because it's left-tailed, it's going to be on the left-hand side negative. And this time we're going to close that drop down, and we're looking at the less than drop down. And our p-value is 0.0013 when rounded appropriately. And we can go down and find our critical t-value. It's the same as what we used before, except for it's a negative because we're on the left-hand side. Okay, so it's a negative 1.833. So let's just go back to our table here on our paper. So there is I recorded our test statistic, negative 4.129. And let's just look at our danger zone here. Let's look, the p-value is 0.010013, which is less than alpha. So we're going to reject using that method. And using the classical approach, our danger zone is here. Because that's our critical t-value. And our test statistic of a negative 4.19 is definitely in the danger zone. It's out here. So these both agree. The p-value is less than alpha and our test statistics. So we don't have to use both every time, but I want you to see that they both match. So our pictures is step 4. And right here is our step 5. So we reject 80. And so our interpretation is step 6. There is sufficient evidence to support the claim that the stock price is growing by or growing, we'll say less than $5 weekly. Okay, that was example 5. So 2 more examples. Oh, actually, there's one more example for this 8.3 examples. It says in 1955, Life magazine reported that the 25-year-old mother of 3 worked, on average, an 80-hour per week. Recently, many groups have been studying whether or not the women's movement has in fact resulted in an increase in the average work week for women, combining employment and at-home work. Suppose a study was done to determine if the mean work week has increased. 81 women were surveyed with the following results. The sample mean was 83. The sample standard deviation was 10. Does it appear that the mean work week has increased for women at the 5% level? So let's go ahead and take a look at this. So step 1, we're going to write our H0 and HA. And so because there's units and the units are hours worked. Okay. So it's means, and they think it's 81, because once it starts talking about the sample, remember, this is our evidence. So this is later in our test statistic. And they propose that it's an increase. Oh, I'm sorry, it's 80 is the mean. 81 women is our sample size. So they propose that it's more than 80. The alpha level of significance is 0.05 again. And our test statistic is going to be our sample mean of 83, subtracting 80 over standard deviation of 10 divided by the square root of 83, 81, because that's our sample size. Sorry about that. Okay, so our step 4 is our picture. Because it's a greater than, we are shading on the right. And I'm going to do the p-value method. So we're looking at the probability that it's greater than 80. Actually, sorry, greater than our sample size of 83. And so step 5 is our p-value on the left, always compared to alpha on the right. So let's go ahead. And I'm going to show you the program again, because the program works every time. It's great. Sample size was 83, we said. I keep saying that wrong. Sample size was 81. Oh, too many 80s in this problem. Our sample mean was 83. We're testing M0 is 80, and the standard deviation was 10. Okay, so our test statistic was 2.7, but we want the p-value. So I'm going to go down here, and it's a greater than, so I'm going to use that drop down. And our p-value is 0.0042. And so there's our p-value. I wrote out our test statistic, even though p-value is what we're going to use to decide. Versus the alpha, it is less than, so we do reject H0. So in step 6, we do reject H0, so there is sufficient evidence to say that the 25-year-old mother works more than 80 hours per week with her job and at home duties that she does. So catch me back for lesson 8.4. We are going to run hypothesis tests for proportions. Okay, reach out if you have any questions.